Number 2. The sine is 2 times square root of 14 over 15. The cosine is 13/15. The tangent is 2 times square root of 14 over 13. Cosecant is 15 times the square root of 14 over 28. The secant is 15 over 13. The cotangent is the 13 times the square root of 14 over 28. Number 4 is the sine is 12/37. The cosine is 35/37. Tangent is 12/35. Cosecant is 37/12. Secant is 37/35. Cotangent is 35/12. 6. The sine is 6/7. Cosine is square root of 13 over 7. Tangent is 6 times the square root of 13 over 13. Cosecant is 7/6. The secant is 7 times the square root of 13 over 13. Cotangent is square root of 13 over 6. 8 is sine is square root of 17 over 17. Cosine is 4 times the square root of 17 over 17. Tangent is 1/4. Cosecant is the square root of 17. Secant is the square root of 17 over 4. Cotangent is 4. 10, sine is square root of 13 over 7. Tangent is square root of 13 over 6. Cosecant is 7 times the square root of 13 over 13. Secant is 7/6. Cotangent is 6 times the square root of 13 over 13. 12 is, the sine is 3 times the square root of 7 over 8. The cosine is 1/8. Tangent is 3 times the square root of 7. The cosecant is 8 times the square root of 7 over 21. Cotangent is square root of 7 over 21. 14. Sine is square root of 17 over 17. Cosine is 4 times square root of 17 over 17. Cosecant is square root of 17. Secant is square root of 17 over 4. Cotangent is 4. 16 is sine is 1/6. Cosine is square root of 35 over 6. Tangent is the square root of 35 over 35. Secant is 6 times the square root of 35 over 35. Cotangent is square root of 35. 18. Cosine is the square root of 105 over 13. Tangent is 8 times the square root of 105 over 105. Cosecant is 13/8. The secant is 13 times the square root of 105 over 105. The cotangent is 105 over 8. 20 is 6.5. 22 is 17.5. 24 is 22.2. 26 is 71.2. 28, A is a triangle with 18 degrees here, and then the height there at 3.5 feet, 90 degree over there. We can look at it more if we need to. 28B is 11.3 feet, and 30 is 190 feet. Did we go through 38 or did we go through 30?
38.
38, okay. Number 32 is 48 degrees. Oh yeah, because we need, yes, of course we did. 34 is 81 degrees. 36 is 46 degrees. And 38 is 69 degrees. What questions do we have?
A lot.
Okay,
Yeah.
let's
Can
pick
I
one and go.
Lowest number to biggest number?
Huh?
Lowest number to biggest number?
We can certainly do some of that.
Start with 6.
6 is fine.
Will we just be reviewing homework today?
Don't know yet. Possibly.
I have a lot of questions.
Well, this is a brand new topic, possibly, so. Okay, we are supposed to write the exact values for all 6 trig functions. So, sine, cosine, tangent, cosecant.
See, I thought this was easy, but I'm doing probably something really stupid and wrong. Because I understand the concept, but I'm still getting very wrong numbers.
I have a guess as to what you're doing, but we'll find out whether my guess is accurate.
You're probably accurate.
Okay. What is our acronym?
So, don't.
SOHCAHTOA.
Just
Yeah.
don't understand. I'm gonna have to go home and read that one.
So the sine is what over what? In this.
30 over 35.
No, in this.
Wait, what? What was the question? I'm sorry.
What is it? Opposite,
Opposite
adjacent,
over hypotenuse.
opposite over hypotenuse.
Oh, I see why that's helpful.
Only 5.
Good.
Okay.
Good. Yay. So, what's opposite of the angle?
30.
30. And what's adjacent? I mean, hypotenuse.
35.
35. Does that reduce?
Yes. Reduce 6 seconds.
Oh.
Okay. Cosine is adjacent over hypotenuse. What's adjacent?
5
Times square
times the
root.
square root of 13.
And the hypotenuse is still 35. Does it reduce?
Yes. Square root of 13 over 7. 5 by 5, 5.
And you got that by doing the.
Dividing the top and bottom by 5, yeah? 5 divided by 5 is 1. 35 divided by 5 is 7. Just reducing fractions. Same as this. It just has this hanging out, right? Tangent is opposite over adjacent, so that will be 30 over 5 times the square root of 13. We can't have that square root of 13 in the denominator. What do we need to do?
Multiply the whole thing by.
Square root of 13.
Square root of 13 over 13. We can also go ahead and like pre-reduce a little, right? And turn this into 6 and 1, right? And then I'll go ahead and write it all the way out because we can.
I think part of the reason I got it wrong is because I said that 35 was the hypotenuse and 30 was the adjacent, and 5 times.
Yeah.
Yeah, so what I think you were doing is you were looking at the arrangement of the picture. You got to make sure and look where the angle is. Because in some of the examples, the angle was right here, and so you're thinking the bottom one's always the adjacent. So you got to look relative to the angle. Because I think that's what I guessed, and I still think that that's probably the main issue. Make sure you slow down enough to see the bits.
So on number 4, you got hypotenuse, 37 is hypotenuse, 35 is adjacent. Because of the
Yes,
angle.
yes.
Okay.
Yeah, 12 is the opposite.
That makes sense. Then we just multiply the whole thing by the square root. We don't do the number connected to the square root.
What?
So like, would be just
Mm-hmm.
to get rid of the square root.
Because square root of 13 times square root of 13 is the square root of 13 squared, right? So it just cancels. And then cosecant will be 7/6. Secant will be 7 over the square root of 13, which we'd have to rationalize, right? And cotangent would be, might actually be easier to think about it like this one, flipping this one over. So square root of 13 over 6, right? Okay, what other questions do we have?
10.
10.
Yes, I agree.
Noise low H.
Good.
Sorry, whoever watches this for the chewing. You'll get over it. Or you won't, and it'll be fine. What number did we just do?
6.
Ah, yeah, it's almost the same triangle that we just did, but not quite. Okay, we're supposed to use this information to find the other 5. What do we do?
So first we're going to draw a triangle.
I agree. Drawing the triangle is gonna help us out a lot.
And then draw the theta in all the corners. Alright, and then since it's cosine, I know it's adjacent over opposite, so the adjacent.
These
I mean,
are
hypotenuse,
Mhm.
sorry.
That's
I
okay.
read the H and I said opposite. for some
That's
reason.
fine.
And then we're going to do a tag right there.
I agree.
So it's going to be 6 squared plus b squared equals 7 squared. So then we move over 6 squared.
Right?
Sorry.
Anything unreasonable there?
Okay, so the way I did it is correct, I think.
And then you're just fine over points.
Mm-hmm.
Okay, I think I know why I messed up.
Good.
I messed up on 10 because I forgot that hypotenuse is always C,
Mm.
and I plugged it in AB.
Mm-hmm. So then the sine will be square root of 13 over 7, etc. Right?
Yes.
What other questions do we have?
Where'd my thing go? 20.
20.
Oh, wait, 18 first.
Sure.
Wait. I don't think I need 18, just kidding. Well,
So many of these wrong because of that. I need 24.
Okay, let's do it. 20. Four.
let's go ahead and do 18. Well. Oh yes, this is a good idea.
Okay. We're supposed to solve for x, round to the nearest tens if necessary. What do we do?
I don't know, but then that's that.
Okay, so we start with, or we should start with, which trig function is happening in this problem?
In order to get x over 40, it's either to have stuff in the numerator, we're going to need opposite over adjacent,
Therefore,
tangent.
tangent.
That's
So,
why I messed it up, I didn't put tangent instead of tangent.
And you figure that out just because that's what
opposite and adjacent,
Okay.
because TOA. So the tangent of 29 degrees equals x over 40. What do we do next?
Multiply both sides by 40 over 1, or get rid of it in denominator. So you have 40 tangent.
So make sure that in order to get the decimal equivalent, and we know we want to do that because it tells us to round if necessary, right? You got to make sure that your calculator is in degree mode.
Yep.
Oh yes. I'm sure we can do that one.
There is.
and then also I have a logistical question. What do we do if it's cosecant, secant, or cotangent, because there's not a button on that on the calculator, and I looked up a way to do it, but
It isn't any of those.
For different problems.
I know. Let me finish, sorry. It's never any of those. Never use those on these. Because what are those? Where do those come from? You know, it's in there.
I don't know.
You do? What are they called? Go back to your notes and look. What are they called?
I figured out to change it to degree.
Reciprocal?
They are reciprocal functions. So what is cosecant? How is it defined?
1/sine.
1 over sine. So you never have to put those in on these, because if it's cosecant, then it's also sine. Does that make sense?
Vaguely, but I don't know how to solve it if the x is in the denominator.
That's a different question. But is there one specifically that's that way? If you don't see one, I can find one.
20, 22, 26.
'Kay.
28, all of them except for 4.
It's great. It's great. 20. Easy money. You got this. So on 20, looks something like that with a 57 and an X, excuse me, and a 10. What trig function are we talking about?
Tangent again.
Tangent again. So we got the tangent of 57 degrees equals 10 over x. Uh-oh. X in the denominator. What do we do?
I don't know, I got caught.
What would you guess you might do? What are your guesses? Is that
Flip over both sides.
that is possible actually.
Multiply everything by x.
So you could flip over both sides if you want to do it that way. I'm going to do both of your things. And you would have 1 over tangent of 57 degrees equals x over 10. You could do that. You could also do what Aiden said, multiply both sides times x. I'm just kind of showing that you're gonna end up the same thing either way. Either way of thinking it algebraically. So x times the tangent of 57 degrees over here equals 10. What would we do next over here?
What did we just do?
You have to apply each side by 10, right?
Mm-hmm. Times 10, and just like you were saying before, it's 10 over 1, right? So this one turns into x equals 10 over the tangent of 57. This one, you divide by the tangent of 57, and you would end up with 10 divided by the tangent of 57. You could also, by the way, think about it as a proportion and cross multiply. And do x times tangent of 57 gives you x times tangent of 57, and 1 times 10 gives you 10, and then you divide and multiply. Either way, you'd end up doing 10 divided by the tangent of 57 ultimately to get 6.5. Easy money.
How do we put our calculators in degree mode?
It's going to be under the mode menu. There's almost certainly a mode menu. Did you find it? No.
No.
Okay. In here, maybe setup. Let's see. Yeah, I was right. Maybe. Yeah. Okay, so in this one, it's not a mode. That's a TI thing. So just because you're going to be doing it in regular calculation thing, and it's probably actually in anywhere. This might actually work from anywhere. You go to setup, and then right now it's in radians. You got to go down and change it. Oop. You don't push enter yet. You go down, and you probably hit degree. Now you hit enter. And now it's in degree mode. So now if we hit the sign of 30, 30 divided by 10 of 57 equals 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. 6.5. Where's the sign? Right there. Sine of 30, it should give us a half. Beautiful.
Question, is this how you draw the snowboarding ramp?
Is that how you draw what now?
The snowboarding ramp?
Let me see.
Degree is in
Let me see which problem we're talking about. Build a snowboarding ramp with a height of 3.5 feet and an 18-degree. No, it would be, so it's a degree of incline, so it's from the base to the top. So it would actually be this one.
I did do that, and then why did I get the problem wrong?
I don't know. What trig function, let's see, what does it actually ask for? Let me see. Length of the ramp. So what trig function did you use?
Sine?
It wouldn't be sine. Oh, wait, just kidding. Let me make sure I'm reading it right. Let me make sure. Hold on. Yeah, it would be sine. You're right.
The length is going to be the hypotenuse, right?
Yes. Yes.
So one hypotenuse.
Yeah, so the sine of 18 degrees equals 3.5 over x.
Is there any reason to take my calculator out of degree mode, or?
Well, the next lesson you're going to learn about radians, so yeah. Okay, did we get all our burning questions answered?
Can we go back to number 6 really? No, actually, I figured that out.
Good.
Yeah.
Have you watched this lesson video? Did you watch Thursdays?
Yes.
Good. Good.
I think the biggest thing for me is just fractions that you have to.
Broccoli
I
keeps.
just heard you wrong when you were describing how the triangle was built. Without the saying right, and I was the only thing that I marked that minus wrong. I don't know.
It seems like you've got the things that you had twisted all straightened out, right?
Yeah.
Good. Let me get some water because this broccoli keeps trying to kill me.
Can we do 36?
Maybe. Yes, we can.
What did
36 is what he said. What trig function are we talking about?
Jason, cos.
Cosine. True facts. To find the angle, though, what do we need to use?
Do we need to get the other side?
-1 cosine.
Yeah, the inverse cosine.
Why?
Because we're looking for the angle. And you punch in your calculator and push enter.
Okay.
And you get 46 degrees.
What's the math that's the no calculator portion?
The exact, special right triangles. 30, 60, 90, and 45, 45, 90. That chart you have to know.
Okay, what's the answer to 30 again?
30 was 190 feet
How do we get there?
with math.
Thank you.
You're welcome. All right, this is gonna be the last one. Then we're gonna do the next lesson. Okay, paratrooper encounters strong winds. than anticipated while parachuting from 13,000 feet. So we've got 13,000 feet.
It's at 13,550 feet.
Oh, thank you. 50. Causing him to drift at an angle of 8 degrees. They gave us a nice little handy picture to make sure we understand what they're saying. How far from the drop zone will the paratrooper land? So, this one.
I was looking for the wrong X.
Okay. Lesson 4.2. Degrees and radians. I love radians. And I know that degree measures are in your brain, and I know you're used to them, and I know you can tell me, like if I told you to hold your hands at a 45 degree angle, you would do, that's 90, but yeah, you would do that. And so I know you understand them in your brain, and I cannot encourage you enough to not just translate to degrees from radians every time. To learn to use radians because they're so nice. They're so nice because if you know the denominator of the fraction, then you know what the thing is, and radians are great. Most of you are not going to listen to me, and you're always just going to convert them, and that's fine. And I would encourage you to use them because they're amazing. Okay, so we start here. Where is my marker? We start with this.
It's lesson 4.2.
It is. This is 4.2 degrees and radians. 4.2 degs and rads. And we start here. We start with our old standbys, yeah? The positive x-axis is the beginning of our circle. This is 0 degrees. When angles are at standard position, which is how we usually want them. If they're not, we put them there later, okay? So this is how many degrees? Yeah, because we're going around counterclockwise. Right? So this is 90 degrees. Which would mean, what?
Just talking to myself.
Okay, good. And how many would this be?
180.
180 degrees. And then this would be how many?
270.
270.
0 plus 360.
And then we go all the way around, it's also 360. It's also more than that because we can keep on spinning around and around and around, and we'll talk about that more later. And we also have our other nice special things, right? We have some 45 degree things. This one would be 45 degrees. This one would be how many degrees?
135?
It would be 135 degrees. And then this one would be how many degrees?
225?
215, right?
No, 25.
Oh yeah, 45. Why am I adding 35? We don't know. You don't know.
225.
Now I'm writing 45 because I just said 45. That's what we're looking for.
Why do numbers?
I don't know. Why do numbers number? Because people need count things. What would this one be?
315.
315. That's where the 15 was in my brain, huh? And then we have other special things, right? We've got some that are kind of in these zones, right? We've got some here. And then some here. And then some here. And then also here. These are going to correspond to those special right triangles, right? Because these are special. They get a place on our, what's going to be the unit circle eventually. Yeah. So this one is 30 degrees. This one is 60 degrees. So what's this one?
120.
120 degrees. And what's this one?
150.
150 degrees. What about this one?
210.
Wow, 210. And this one?
240.
And this one?
300.
And this one?
330.
330. Everybody following where the numbers are coming from? Everybody following how the numbers are numbering? Good. So, let me change colors a little. When we're counting, when we're going clockwise, these angles are positive angles. Right? So, going around counterclockwise, starting at the same place, those are negative angles.
It always confuses me that counterclockwise is backwards one.
Right? Seems counter. Huh? Seems like a double negative. So, if I was talking about a negative, or at what would 330 be?
So that
30 degrees?
Negative 30 degrees, right? And 270 would be the same as negative 90, right? Et cetera, et cetera, et cetera. All the,
You said clockwise is positive, counterclockwise is negative?
yes, but it's clockwise and counterclockwise of graph, which is just goes 1, 2, 3, 4.
yeah. Going counterclockwise, that's why I've got the arrow going that way, is positive angles. Clockwise is negative angles. And what, yeah, so if you remember, what quadrant is this?
1,
Right? What quadrant is this? 2, etc. Yeah?
3.
Right? So the angles, the positivity matches our quadrant numbers, right?
No, you had it correct the first time. He said it wrong the second time. Because counterclockwise and clockwise is weird on the graph.
Okay, I guess I'm not understanding.
Okay. Quadrant 1, 2, 3, 4. Going in that direction, that is clockwise, even though it's technically counterclockwise on an actual clock. So then going like 1, 4, 3, 2, 1, 4, 3. That would be clockwise on a graph, but counterclockwise. No, that would be counterclockwise on a graph, but clockwise on an actual clock. So it's backwards.
It's not
from
backwards.
an
No, it's not.
Yes, it is.
12, 1, 2, 3, 4, positive. Like, what are you talking about?
No, that's the negative one. We were just saying that. The negative is drawn going counterclockwise, going clockwise on a clock.
Oh yeah, it's not clockwise and counterclockwise. Positive is clockwise. Forget clockwise. Positive goes that way, negative goes that way. Deal?
Okay, positive goes quadrant
Left.
1, 2,
Positive
3,
goes
4.
left.
Negative goes quadrant 4, 3, 2, 1.
Yeah.
Positive goes left, negative goes right.
Forget the clocks. I can read a clock. Who said I can't? Continuing. Now, as degrees. Radians are cool. I honestly have no idea where degrees came from, so I can't answer that. But radians, I can tell you where they came from, and it makes sense.
1/360th because it was a very effective number as which to divide by.
Somebody just picked that number.
It was a very effective number to which to divide because you can divide it into very small sections that are
Yeah,
like.
but it could have been 530, or it could have been 100, or it could have been...
No, it's because 360 you can divide into a bunch of like numbers that are whole numbers. They can be divided into 60, into 30, into 5, into 2, into 10. Into
And a lot of
15.
you can do like, yeah. I'm telling you that there are other numbers that could be picked. It's probably that and something else. But I don't know what all the things are, and I don't frankly care because radians are cool. So let's learn what a radian is. Radian is based on the circumference of a circle.
Draw a circle.
Yeah,
Okay.
more or less.
Can I steal your cup, Sean?
Yeah, no, but you can borrow it.
Just kidding, it's wet. That would be better.
Just freehand circle, it's fine.
Totally fine.
It's notes.
You mean you don't carry a circle around with you, Garrett?
I'm sure there's a circle somewhere in my backpack.
Now, we're going to cut a pie piece out of the circle to illustrate what a radian is.
Like pi is in the tree or pi is in the number?
Pi is in a pie piece, which would be like a shape.
Is a radian like a segment of degrees?
No, radian doesn't have anything to do with degrees, except it does.
Okay.
What is this called? Assuming this is the center.
Radius.
This is a radius, so we label it with R. Well, cool beans. This is an angle. So what do you think he's going to get labeled with?
The angle thing. The delta.
How about, not the delta,
Theta.
Theta.
the theta, the other Greek letter.
So only like 27 of them.
And this is S. So that is the arc length that's cut right there. So that's the sector length. Yeah?
Yeah. I only remember this from geometry.
Nice. So in radians, the angle is defined as angle in radians. I'll put rad down here just for clarity. Angle in radians is defined as the ratio of the sector length to the radius. Now for this next little bit of conceptual gymnastics, I wish I had concentric circles that I could draw. I'll do a little one. I was going to do a bigger one, but I'll do a littler one. That'll work. Does it have stuff in it? No. Wunderbar. Great. Assuming the center is the center, assuming those are concentric, I have a question for you. It is a rather simple question. Does the angle change?
No.
No matter how big or how small the circle is?
No,
It does not. It does not. So, let's see if we can convert between degrees and radians using a little thought experiment here.
Oh, so we use the angle to convert them.
to convert them back and forth. But it's nicer. So I'm going to give you a there's two ways. Well, there's only one way, but there's one intuitive guesstimation thing. Yeah. So if you're looking at an angle on a page and it doesn't have the degree symbol, then the angle's in radians. Okay, that's the real way to tell. Also, if you have an angle listed on the page and it has a pi in it, like not a pi piece, but the Greek letter pi, it's probably in radians because we leave radians based in pi, and we like pi to stay when it's in radians. So let's do a little bit of looking at our little circle here. How many degrees is this? 180 degrees, yeah. That's 180 degrees. Now, how many degrees is this one?
360.
360 degrees. How many pies is it? How many pies is it all the way around?
1.
2 pi r.
2 pi times the radius. If the radius is 1, then how many?
What is C?
Circumference. If the radius is 1, then how many pies is it?
2 pi.
2 pi. So this is 2 pi radians all the way around the circle. So this one would be how many pi?
1 pi.
1 pi radians. And this works no matter how big the circle is. We can turn it down to a unit circle. We do unit when we do the unit rate. Our goal is to get that denominator a 1. You probably learned that back in pre-algebra a long time ago. Probably. We're trying to find a unit rate. We want that denominator to be 1. A unit circle is a circle with a radius of 1. So we go down to that, and we can build. Before we do that, let's do a couple of these examples, and then we shall build a unit circle. And then we'll give you another formula. You know what? Forget that. I'm going to give you all the notes first, then we'll go back and get as many examples as we can get. Let's do it in that order. That way we have all the notes and then see from there. Okay. So let's build this in radians. Yes. We are going to build the unit circle, which might be the next lesson, but yep, it is the next lesson, sort of, part of it. We're going to build it now, and we're going to learn the conversion in a second. Okay. So this is in degrees. Yes, yes, degrees. Because we're doing this in this order because we're doing it in person. And it's nice to get some intuition first. How many radians would this be?
0.
0 radians. This is in radians.
But would it also be 2 radians? Because it's also
2 pi radians.
2 pi radians.
Yes. Okay, so this, we already said, 180 degrees is how many radians?
1 pi.
1 pi radian, so this is pi radians. How much would this be?
Pi over 2.
Be half a pi, that's true. Pi over 2. Yeah. How much would this be?
3 over 2 pi.
Yeah, so 1.5 or 3 pi over 2, right? 3 pi over 2.
The numbers right now. Pi.
Right?
And then 2 pi.
What? Yes, and then 2 pi, yes. All the way back around would be 2 pi.
3 pi over 2?
Yeah, because it's 3/4 of the circle. 3 pi over 2. 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 3 pi over 2.
Yeah,
Okay,
it's,
I just do 1 and 1
Could it
half.
not be over 4?
no, don't do that. Keep it in proper fraction, please.
That makes
I promise that's what you want. I promise that is a better plan. I know it doesn't seem it, but it is.
We should write 1/2 pi or pi over 2?
Pi over 2. Okay, now, what would this be?
Oh, gracious.
Okay, so it's 1/8. Is that correct? No, 1/4 of a circle. No,
So-
so that's a fourth, so that's an 8. So
Look, think about it.
pi over 4.
It would be pi over 4. You got there really complicatedly. It's a fourth of this one, right? Right? It's a fourth of 1 pi, right? So,
Yeah.
but yes, this is pi over 4.
Somebody needs to do the complicated one at some point. That's how math
Right?
is made.
Is well, yeah, some of it. What would this one be?
3 pi over 4.
3 pi over 4, because it's 3/4 of 1 pi. And then this one will be pi plus a fourth, yeah? So 1 and 1/4, how does that, what's that an improper fraction?
5 pi over 4.
5 pi over 4. I want you to notice something about these denominators, because this is the power of radians. All these denominators match. I want you to, well, yes, because the other two formulas are easy. In your calculator, switch it to radians mode. Quickly.
Okay.
I want you to punch in radians mode the sine of pi over 4.
With that.
Yeah, some fraction, right? Actually, no, that's fine. With that in a minute.
Square root of 2 over 2?
Square root of 2 over 2. True, which is what that is.
My calculator's not good to me in that.
Okay. Now punch the sine of 3 pi over 4.
Same thing.
Square root of 2 over 2?
Same thing. Now punch 5 pi over 4. All students take calculus, yeah.
What
Negative
about
that.
getting the square root of 2 over 2 from?
I don't know. I'm not.
His calculator is doing it in MathPrint, which is nice. Your calculator would do that too. You got the same thing.
Yeah, I just didn't have time.
You got the decimal version. So you got the same thing, but negative. We'll learn why that later.
What was the number you said again?
I'm not getting negative.
When you put 5 pi over 4?
Sine pi.
Yeah.
Yeah, I'm not getting negative for that.
Are you in radians mode?
I thought I put it in my page.
You have to put it, I said that already.
I thought I did.
It clearly says deg.
Uh-oh.
What would this one be?
7 pi over 4.
7 pi over 4.
Oh, now it's putting square root of 2 over 2.
Ah,
Fancy. Mine is nothing nice to me like that.
you can probably change in the settings whether it'll automatically do that, which one it'll default to. It will do the conversions for you, but
Yeah,
Because it's 1 and 3/4?
yes, sir.
So, okay.
Yes, sir. That's right.
I can't do that.
Good.
I understand.
This one's hard to eyeball.
Okay. So let's think through what these would be. So how does 30 degrees relate to 180 degrees?
You have to multiply it by 16. No. You have to multiply it by 6 to get 180.
That's true. So it is, in fact, a sixth of 180. So 30 degrees is pi over 6 radians. What about 60? How does it relate to pi?
Pi thirds.
Pi over 3. So what's this one going to be?
2. 2 pi over 2.
What?
Oh no, that's not 90. That's 120. That's That's more than one
It's
half.
2/3. So it's going to be 2 pi over 3.
2 thirds.
2 pi over 3.
Or would be 5 pi over 3.
Okay. And then
What would the next one be?
5 pi over 6. Or is that completely wrong?
That's not completely wrong.
Okay, I'm somewhat getting what we're doing.
What would the next one be?
Good lord.
Oh, I'm missing. Am I missing something? Oh no, I'm not. I just
7
drove
pi
it.
over 6. So then the next one will be 4 pi over 3. And then 5 pi over 3.
What did you say? I'm sorry.
5 pi over 3. And then 11 pi over 6. I shared the things.
What's the sine of pi over 6 in your calculator as long as in radians mode?
One half.
Push sine of 11 pi over 6.
Negative 1/2.
-1/2. Push sine of 7 pi over 6.
Negative 1/2.
What do you notice?
Some odds and evens.
Well, wait, what? Stop. Go back. What are you saying? Odds and evens? You mean positives and negatives? Is that what you meant?
Yeah, the odds and evens are.
They're always 1/2.
Oh.
Everything with a denominator, if you do the sine of anything in radians with a 6 in the denominator, it's going to be 1/2. And then once you learn that all students take calculus, you'll be able to know whether it's positive or negative. Well, you'll learn that soon. Wow, what is that blood curdling scream? It's terrible. Okay, you need a couple formulas. Have you figured out the conversion between degrees and radians yet? That's a very simple formula. Very, very simple formula.
It's in my brain, but I don't know how to express it.
To convert from degrees to radians. Which page am I on? What am I doing? Of course, it doesn't matter because I look at that and I say weird things and write weird things, and eventually we'll get it on there. From degrees to radians. And then over here, from radians to degrees. If we start in degrees, we have to multiply times pi over 180 will give us radians. So to go from radians to degrees, what are we going to have to do? multiply times 180 over pi instead. Now let me tell you how I remember, like, in a moment of panic, which one's which. Whether you do 180 over pi or pi over 180. What did I tell you about radians? I gave you this tidbit early in this lesson. We almost always write in radians, they're almost always in terms of what? Pi. They're almost always in terms of pi. So radians, if we want radians, then the pi is going to be on the top because he's probably going to stay in. So to get radians, you multiply by pi over 180. To get degrees, we want the pi to go away so that pi is on the denominator. That's how I kind of remember it in, like, making sure of what I'm doing. Okay, here are a couple more formulas that you need. These are physics things. Aren't you excited?
I'm so happy.
This is like kind of late-ish in physics because we get to circular things. I'm going to give you 3 formulas and then I'm going to tell you can walk out the door. Okay, first formula, to find the arc length. These formulas, in order for these formulas to work, your angles have to be in radians. Okay? You might want to make that as a note. Okay? So for arc length, the length S equals the radius times the angle. Make sure this is in radians. Next formula. Linear speed.
Does this also need to be in radians?
Yes. They all do, all of these. Linear speed, so that's in a circle. That's how fast it's traveling on the outside in physics, right? So how fast this is going. So that's why it's called linear, because if we stretch it out into a line, it's linear speed. Linear speed is calculated. We use v for velocity. And I'm going to add a vector symbol because physics is the length it's going to be traveling divided by the time. Which makes sense if you've had the very beginning chapters of physics. Okay, and then next formula, if you want to find an area of a sector, so talking about like the pi piece, yeah? How big the piece is. How do you find the area of a whole circle?
Pi r squared.
Pi r squared. So it's going to be similar to that. Area of a sector
Pi r squared over section.
is 1/2 r squared times the angle. So it's kind of like area of a circle and area of a triangle shoved together with an angle, right? Oh no, that's it. I thought there was one more formula, but that is it. Goodbye. Oh, except I need to tell you your homework. Homework. Oh, one thing we didn't talk about. Okay, so page 238. 2 through 8, if I gave you a video, because it's easy to do. This is evens. If I give you a video, that's assigned. If I don't give you a video, that's not assigned. And then is assigned is 10 is assigned no matter what, is 10 through 40 evens.
On the same page?
Yes. Now goodbye.